Hello. Okay. So, good afternoon, everybody. Thanks for coming. Thanks for attending. You are at the industrial production of biofuels tutorial, and our main guideline is learning through experience. My name is Paulo Seleguim. I'm from the University of São Paulo, and the three speakers, first one, myself. I'm going to be talking about technology assessment. And then Professor David Caramonte from University of Florence, he's going to talk about process modeling and simulation. And Dr. Marcos Watanabe from CTBE, Simulation and Technical Economic and Environmental Analysis. First comment, the event is being live streamed through this channel on YouTube. And after the tutorial, the 3 videos will be made available for you if you have problems sleeping and you want to, okay, some remedy for this problem, okay? This is an experimental initiative, but well, let's hope everything goes all right, okay? So without further delay, I'm going to start my tutorial, technology assessment, and I'm going to try to inform you on how to measure the maturity of a certain technology and, of course, relate it to biomass conversion to biofuels and bioproducts. Okay, so this is my particular topic. First, let me describe the problem. The problem, you know, is that renewables compete with fossil energies. Both in economical and technical aspects. And this is related to our lifestyle. You know, 15,000 years ago, we needed energy for what? Just for our metabolism. Our metabolism needs around 120 watts, which is, I don't know, 3 or 4 lamps here in this room. And today, an average citizen consumes 3,000 watts. That's more, 20 times more. So, and the metabolism is the same. So the difference is related to our lifestyle. We need cell phones, we need refrigerators, we need microwaves, illumination. Public illumination is a very disruptive technology in our society. We need, well, computers, we need heating, air conditioning, we need, I don't know, transportation, we need agricultural machines, energy to plow, energy to harvest. Well, we need, to do this, we need energy, we need to make energy carriers, and we also need chemical compounds. These two were taken from the underground today. Oil, coal, and gas. We're pumping these substances from the underground, okay, and then we transform into energy carriers and or chemical compounds in an industrial conversion unit, let's say like this. The problem starts now. The problem is that when, for instance, when we want to make energy, generate energy from these compounds, well, we use several chemical reactions, for instance, a combustion reaction from which we generate heat, which we can convert to electricity, but the problem is not here, the problem is here, okay? This CO2 is going to end up in the atmosphere, and it's going to change the chemical constitution of the atmosphere, and, well, you know all the consequences. Okay. A possible solution for this is to try to build a neutral economy, a neutral in terms of carbon footprint. So instead of getting our feedstocks from the underground, we can get carbon atoms from the atmosphere through photosynthesis, for instance. The energy necessary for this, you know, comes from the sun. Roughly speaking, 0.3 kilojoules. If you want to remove, if you want to capture half gram of CO2, you need 0.3 kilojoules. Okay, this is a very rough number, but it's correct. So if you build your feedstocks through photosynthesis, you can convert then these biomass feedstocks to energy carriers, electricity, gasoline, ethanol, and so on, and also chemical compounds. When you, let's say, re-emit this CO2 to the atmosphere, no problem, because it was present in the atmosphere in the first place. So, theoretically speaking, it's a neutral cycle. Another possibility, very interesting one, I'm going to show you. I hope I can convince you, because the idea may be quixotic, but you can try to, instead of re-emitting CO2 to the atmosphere, you can take a little amount of this energy surplus and instead of re-emitting CO2, you can transform this into a supercritical CO2, which is a carbon carrier. It's considered a carbon carrier, and it's very well suited for underground injection. So actually, you're pumping CO2 from the atmosphere to the underground, okay? And the energy necessary for this comes from the sun, okay? So we know already that this is viable in terms of technologies and energy balance. You need to you need about 20 to 30% of this energy surplus, okay? But the problem here is it must be also economically viable. Okay, so the problem is that the loss of revenues from electricity must be compensated by carbon credits. I say actual because these carbon atoms, they were here, free in the atmosphere, and they're going to be in the underground, okay? Trapped in the underground. So we know it's viable from a technical point of view, but it still have to be economically viable. So that's why I used to say it's a quixotic idea. Okay, well, I'm just describing the problem. So what people thought would happen in this scenario, the transition from a positive carbon to a neutral, and eventually to a negative carbon footprint. That's known as the Hubbard law. So the idea was that, 500 exajoules, exa is 10 to the 18, okay? It's the average world energy consumption. With the decline of oil fields and coal fields, renewable energies could take the place, okay, and become predominant in a certain future. And this transition would be happening between these dates here, okay? So that's what people thought would happen a few years ago, or 2 or 3 decades ago. What really happened was this. It's true that oil fields, they get older, they don't produce anymore, but the problem is that you keep discovering new oil fields, new gas fields, and also you keep finding, keep developing new technologies that makes known oil fields that were not viable. Okay, so that's exactly the case of shale oil and gas, bituminous sand. So these reserves here, these amounts here were not viable. Okay, we would know how to make oil or gas from shale. Okay, but it was too expensive. New technologies rendered this viable, so it took the place. So what really happened is that the availability of fossil resources, it's okay, no problem, okay? And renewable resources or renewable products are having a hard time taking the place here. And mainly due to lack of economicity. And that's one of the focal points of this tutorial today, okay? Well, I think I described in a few words what is the problem, but there's also what I can say, it's a problem within the problem. Biomass conversion technologies must be competitive enough to displace fossil fuels. But the problem is here. How much is enough? How do we measure this competitiveness? And that's the point. That's exactly the point of my talk. Okay, so I'll be talking about technology assessment. That's my main focus. Okay, I'm going to be talking about the scale. How can we measure this maturity of a certain technology? I'll be talking about technology readiness levels, or TRLs. I'm going to try to give a brief history and definitions. History is important because some terms and some concepts you can only grasp the meaning if you know how this evolved. Okay, we're going to try to make a tutorial within the tutorial. Okay, we're going to try to give you some tools. Okay, and then well, that's the first part of my talk, and I'm going to talk about technology deployment, and especially talk about risk management. Okay, so technology readiness levels. Three main guidelines. Okay, first, a TRL is a measure of the maturity of an evolving technology relative to its development cycle. Okay, then whatever this TRL may be, you may build your own TRL. Okay, but you will probably want to follow these guidelines. The second one is identifying critical technology elements. And if you are able to identify these bottlenecks that hurdles your development, you may construct or develop a technology maturation plan. So you can plan how things will evolve during time. And then it must also be a kind of a support decision, okay? By providing a reference framework for understanding of technology status to facilitate risk management, okay, to attract external funding and so on. Okay. So there are some key concepts in this slide. Okay, I'm going to be coming back to these concepts further on, but right now I want to talk about risk management. Okay, so let me try to make an experiment to you guys. Okay. So that's what I say, a tutorial within the tutorial. How much would you invest in this idea? Let's picture this situation. An inventor comes to you and say, oh, wow, I invented this, I have the patent, I constructed a pilot plant, let's say like this, okay? And I tested it's okay, but I need money, okay? How much would you invest in this idea? That's a dramatic pause I'm doing now. How much would you invest in this idea? R$2 in Portuguese. Okay, so let's see what happened, because this actually happened. This is a true story. Okay, 1947, and well, a few years later, they managed to miniaturize this component. Okay, and then, well, you know, several tests on encapsulation. You also need a kind of a board or something to fix these components. So you need what we know now is a printed circuit board, and you need to develop the terminals and so on. Well, and then, well, you know it's going to be a transistor. Okay, and jumping to the end of the story, 40 years later, okay, and with incorporation of other maturing technologies, this brought about the microprocessing technologies, CPUs and so on. Only the processor market, $335 billion in 2015. So you see the potential of this. And if you were lucky or crazy enough to put money in this idea, you would be now, I don't know. Yeah, I don't know. But that's the point. So how can we measure, how can we plan this development, okay? Because, you know, that's the whole idea of TRL. So a TRL actually is, as I mentioned, a scale of maturation of a certain technology, okay? So going to the details, you have, well, 9 levels of maturity. Why 9? Because, well, that's for historical reasons, actually. Okay, so the idea is that the first ones are more related to concept okay? I used to say the idea inside the head of the inventor, okay? So the guy who invented the transistor had an idea, so he's in TRL 1, okay? So he grasps the concepts, he makes some lab experiments to test hypotheses, everything goes wrong, so he goes back to his notebooks and correct his equation, build another experiment and test. So this is cycle, okay? Although the scale is linear, the development, the process is not linear. It has never been actually in history, okay? So you have cycles of development. So in TRL 3, you're sure of your lab experiments, then you go to levels 4, 5, and 6, where we have bigger models, benchtop models, engineering prototypes, where you may be testing, for instance, materials, like in this slide here, okay? And then you go on, you test how this component is going to be integrated to other systems, okay? So you test integration, and well, after a certain time, you went with this, what is a kind of a commodity, okay? So it's going to become a component to be integrated in other systems, okay? So that's the idea. We're going to look in details, all these levels, okay? So basically, basic research, focused research, demonstration, and integration, okay? The idea inside the head of the scientist, and then the process being industrialized and spread on society, okay? And also another important thing is that, well, the process is not linear. It may involve cycles of development, as I hope I passed the idea, but it also incorporates other developing technologies, okay? So in this case, we need, because here you have the transistor and here you have the CPU, processing units, okay? So CPU actually is a trillion, or not a trillion, but a million transistors, okay? But you need miniaturization, you need integration, and of course you need processing. So it's not linear. It may and it should integrate other technologies that are evolving as well, okay? So that's the whole point. Talking about the history of this, the story of this development, you know, things started in NASA. You know, when President Kennedy announced that they were going to be going to the moon, that's a very interesting story because they had exactly 20 minutes of experience outer space in orbit. 20 minutes. And the guy, wow, we're going to the moon. They didn't know nothing. The spacesuit, the fuel, the rockets, the computers, everything had to be developed in 9 years. Okay? So they had 20 minutes of experience, and in 9 years they managed to go to the moon. So in order to accomplish this, they developed this because all technologies were being, invented and implemented and deployed, okay, in 9 years. So they had to have a tool in order to control, to try to put things into perspective, for instance. So things started in NASA. But today you have several, the concept is very interesting, so it was absorbed by other areas, let's say. So the European Space Agency, also the Department of Defense, oil and gas industry, okay, European Commission, US Department of Energy, you have several. As I said, you can build your own, okay? But, well, there are several scales of technology readiness levels, but they are always similar in terms of concepts, main concepts. Okay? The differences will arise in terms of specificities. For instance, some words and some terms are still in the literature for historical reasons. I'm going to pinpoint that when the time comes, okay? So let's see some definitions of TRLs which are, let's say, adequate for our purposes. I'm going to try to highlight some terms here, okay? So TRL1 as I said, it's the idea inside the head of the scientist, and it's the lowest level of technology, okay? And it's actually scientific research. So at TRL1, you have discoveries. You have scientific discoveries, okay? TRL2 is technology starts to take the front, okay? So you're focusing on applications. Well, I discovered this phenomenon, okay? And I know, let me give you an example. We discover the Higgs boson. That's a discovery, okay? It was first discovered in equations. Now they managed to detect this particle. What can we do with this? I have the faintest idea, okay? I don't think anybody has, but we could, let's say, build a time machine with, okay? So formulating possible applications, okay? That's what's going on TRL2. And so here invention begins, okay? So TRL1, scientific discoveries. TRL2, invention begins. So boson of Higgs is, the Higgs boson is a discovery, and the time machine is an invention, okay? So invention discoveries are more related to TRL1 and 2. TRL3, well, things starts to develop, okay? And you have proof of concept. So, research and development activities are initiated. For those of you that are aware or know or have experience with this FAPESP project, PIP, okay? I would say that PIP1, which is for proof of concept, is related to TRL3, okay? So if you go to FAPESP with a PP proposition, I think you should show them that the previous steps are already, okay, settled, okay? TRL4, so validation, still in a controlled environment. So you're going to validate, let's say, the time machine that we are inventing, okay? So you need to test your components in controlled environment. So a pump, well, you're not sure that if the pump is going to work with this kind of fluid, so you start testing components, okay? TRL5, you have what we call a relevant environment, so you test the pump with the fluid in the conditions that you suppose is going to happen during the intended application, okay? For instance, you may be developing a pump for a specific oil, and you may have contamination. You may have sand particles within the oil. So what's going to happen with this contamination? Okay, so this is still in a controlled environment, but it's not exactly the actual final environment, but it's relevant in terms of you see if the thing's going to work. Okay, well, TRL6, you focus on systems and subsystems, still in a relevant environment, okay? TRL5, you start demonstrating prototypes, so it's a small scale of your invention, okay? It may be a power plant, it may be a time machine, I don't know, okay? So prototype near planned operation system, okay? TRL8 actually is the final. If you accomplish TRL8, you've demonstrated that your system, your time machine is going to work, okay? And TRL9 actually, you have proven that things went all well. You see the word mission here, mission operation, okay, or mission operational mission conditions. The word mission comes from NASA. Okay, so mission, it means in the conditions that the application is going to find in outer space, okay? for us, you must adapt to this word, okay? I changed some words here in order to make it easier, but I decided to leave this word here just to link to the history of all this development, okay? So that's the scale, and we're going to, actually, this is happening to us. So, you know, we had this, I don't know who had this idea, or possibly many people did, but, well, you know, we can use these enzymes in order to deconstruct these polymers of sugar and so on, and that's the basic idea, TRL1. Now we have industrial units to try to do this in large scales and to make money out of it and so on. So this happened, you know, both ends of this scale and also the parts in the middle happened and are happening right now. So what have we learned from all these experiments? That's another, let's say, guideline of this, of my talk, okay? Well, so in order to assess, in order to define, if someone comes to you, I know I have this process, I have this chemical compounds, how can you decide if it's TRL 6 or 7? Okay, so I'm going to give you some tools. The basic guideline for a tool to assess the technology readiness level is that two most important words: a consistent and reproducible method of assigning a TRL to a specific technology. Okay, and well, you're not going to be able to avoid this. You have to be based on surveys and polls, and you're going to end up by asking questions to people concerned, to people that understand the situation and live the situation. Okay, well, you can ask bird's eye view questions over evaluation, or you can ask TRL specific. Okay. You also, well, if you ask, you're going to have an answer, possibly. Okay. So you can have binary answers, yes or no, or you can have, I don't know, I think this is 80% true. Okay. This happens. So what's going to happen is, you're going to end up with what we call a fuzzy data set. A fuzzy data set is a set of data that may be contradictory. Sometimes we ask the same question 2 or 3 times, but formulated differently in order to see if the guy sticks with his first answer. Okay, so it may be, well, he said yes, and now he's saying no. So it may be conflictive. It may be lacking. You may have holes inside this set. Well, I don't know. I'm not going to answer this question. Okay. Anyway, the point is, you are going to have what we call a diffusifier, which actually is a set of clever mathematical formulas. You're going to see how clever this is in a few slides. Okay, and the function, the role of this diffusifier is to take this data set and to assign a level. Okay, so it's going to make some calculations with very complicated mathematical formulas. You'll see. Okay, so let's make an experiment. What I say, a tutorial within a tutorial. Oop. Let's imagine a certain installation. Okay, I took one which is not closely related to us. The idea here is that and I'm going to be asking questions about this installation, but the point here is not the installation itself, is the size and the characteristics. You see the size, you see a guy here, okay? You see another one taking a picture here, you see a kind of a reactor here, okay? Heat insulation. You see this is the control system, a table, a computer, and a screen. Okay, so you have an idea of the size of this installation. It's indoors. I hope you can identify here. It's indoors, okay? So it may be heated in winter, air conditioned in summer, hopefully. So you get the idea. Now I'm going to start asking those questions for you. Okay, so let's see. Those are I don't know, a list of questions that we have on our questionnaires. Let's try to answer by ourselves. So you keep thinking about this installation, okay? And let's see this first question. Have basic principles been observed and reported? Yes, of course, yes. Probably someone had the idea and made some tests in lab. Okay, so yes. Has a concept or application been formulated? Yes, of course. They are trying to build, I don't know, fuel. So it's an application, yes. Has analytical and experimental proof of concept been demonstrated? Yes, okay. Well, the first ones are easier, okay. Has a pilot unit been demonstrated in a laboratory environment? By laboratory, I mean controlled environment. Yes, that's exactly the picture I showed you. Has a pilot unit been demonstrated in a relevant environment? By relevant, I mean you start experimenting the actual conditions that you're going to find in the field. Yeah, you can do this in the lab. You can contaminate your feedstock just to test. You can. I used to do this a lot. I add sand to my feedstock to see, to biomass, for instance. I mix with sand or residual sucrose, for instance, to see what's going to happen in the process. So you can try to simulate these actual conditions. So that's what we call relevant environments. So let's say yes. Let's answer yes to this question, okay? Has a prototype unit been demonstrated in the operational environment? No, that's not the case because we're still indoors. That installation is still in the lab. So the answer here is no. Has an identical unit been qualified? Of course not. Okay, has an identical unit been demonstrated on an operational? So all final questions are, the answer is no. So we have yes and no questions. What we need to do is to, so here is the fuzzy data set. Here's the scale. And now what we need is the diffusifier, which I said that was the set of very clever mathematical formulas. Well, it may be a simple rule of 3, okay? So we have 9 questions. We answered yes to the 6th question, so our TRL is 6. That's my diffusifier, okay? It's as simple as this. Another, well, it's 6, but let's test the hypothesis of being 7, okay? Because, well, has it been demonstrated in the operational environment? Yeah, not yet, but we did a lot of tests within our relevant environment. So let's test the hypothesis that is TRL7, and let's try to ask questions related to TRL7, okay? And just to show, you can, in this case, you can answer not in terms of yes and no's, but you can give a percentage, okay? So materials, processes, methods, and so on have been identified. I would say 80%. I don't know if you managed to see the scale, but okay, 80%. Why is that? Why 80% and not 10%? Because, well, materials, I know that the compounds within the reactor, well, I had problems with the first model I built, so I have changed the materials. I selected more resistant materials. So I've been through here. Okay, so 80%. Let's see another one. I'm not going to read all questions, but is scaling complete? Well, I would say 10% because this installation is going to become an installation probably bigger than this whole building. Okay, so it's still very small. Okay, so it's still very small. So I say, well, 10% for this question, and the same for the other questions. Yeah, and then you go to your very clever mathematical formulas, and you end with 6.6. So that's it. That's our assessing tool. You can get simple levels like this, okay, and you can be more specific. But this is very, let's say, reproductive. If you apply the same questions to other players in this area, They may be answering because they have different views of the technology. Some guys are luckier and then they don't have the problems that you had. So, but the idea is that it's reproductive, okay? And you can compare because this is being done to other technologies and space engineering and so on. So you have a very interesting way of making these comparisons. Okay, so let's talk about risk management. Okay, I've been showing you how to assess this technology, and the idea is that technological risk decreases with technology maturity. Okay, so of course it's very risky at the beginning, and by risk I mean the risk of what? The risk of not working. You know, the transistor was invented, but I don't know if you know, but several inventions prior to the transistor, well, were invented and they didn't work because, I don't know, the concept was wrong. So there's a risk. And you have to decide when to put money and what kind of money you're going to put depending on the technology risk. Okay, so that's a, well, empirical observation. If you have more mature technologies, TRL 7, 8, or 9, if you want to invest, you don't need to struggle a lot. Traditional investments like an IPO, it's okay. Okay. The interesting part is here. Okay. So below TRL 7, you need venture capital. Venture capital is very different. Okay. You need people decided or not afraid to take risks. Okay? So if you are between TRL 3 and 7, okay, you make this kind of investment, startup investments. Okay, that's typical of PIP, FAPESP PIP is here. Okay, and if you are below this TRL 3, okay, you need seed capital. Seed capital is like horse betting, okay? Like, it's really a gamble. What you do if you are an investor, you have an investment portfolio and you have, I don't know, 20 investments in this region here. You know that 20 investments, 19 will fail. It's going to happen. It's statistically true, okay? But the one that's going to succeed, they will become a transistor, okay, as I showed you. So this is seed capital, okay, and you see it's very closely related to the technology readiness level, okay. So moving further, I want to talk about now technology evolution. How does technology evolves in time? And with focus in incremental and disruptive leaps. Okay, so let's see how we could do this. Let's try to do it by ourselves. Okay, so let's take this kind of technology, data storage performance. Okay, I'm not talking about those clay tablets with cuneiform writing. Okay, when it started 100 years or even less, but I'm going to be talking about data storage. How do we measure the capacity, the performance of this technology? You can have several types of assessment. For instance, capacity, access speed, how tiny it is, and so on. Okay, let's stick with let's say access speed. Okay, the first, well, my master's thesis is in punched cards. Okay, so and then appeared a tape reel. My PhD I started with tape reels and then I moved to the floppy disk. Okay, so the floppy disk is a very, very interesting development of the tape reel. For instance, in terms of access speed. Why is that? Because if you have a tape reel and you have a data at the end of the tape and you want this data, you have to fast forward to the end, and it's going to take time because you have I don't know, 300 grams, turning very quickly. So it's really a mechanical device. If you have a floppy disk and the data is at the end, well, your pickup is going to the end, it's quite faster. But I want to highlight some points here. First, there's a leap in terms of access speed. Okay, so it's a disruptive evolution. But the old technology continues to be improved, of course. So we had the tape reel, then we had a cassette. It's still a tape, it's still a linear form of data storage, but it's infinitely more practical than the tape reel, okay? So the point is that technology continues to be improved through incremental steps, okay? Mostly associated with experience, economies of scale, and so on. So you have two examples here, okay? Incremental evolution from the tape reel to the cassette, okay? And then a disruptive leap by changing the technology from taped to disk, okay? And if we continue, another point I want to highlight is that the adoption of a disruptive technology causes a quantum leap in performance, okay? But if we continue, another point I want to highlight, I'm forgetting my points, okay? This is very important actually because it's happening today. Competing technologies may coexist for some time, and some is very vague. It may be 1 year, 5 years, or 100 years, I don't know, okay? Yeah, so if you get the idea, we can, well, trace the history. After the floppy disk, we got the CD, the floppy disk evolved to these small disks here, okay? Then we had the pen drive and so on, and now we have cloud storage. Very interesting, and the old technology still coexists. You know, you see the pen drive is evolving to very sophisticated examples of data storage technologies, okay? Oops, sorry. And yeah, that's it. But there's a concept here that I'm not being able to show you in this slide because I'm only talking about performance of technology, okay? I want to talk about another concept that is robustness, technology robustness. How robust is my technology? What do I mean by that? I mean exactly this. You have a technology that works under nominal conditions, okay? What happens if your actual working conditions are not nominal, okay? If they are slightly, if the room temperature, if the environment temperature is slightly different from the nominal temperature, how does the performance of your technology behaves out of nominal conditions? Does it, well, it's going to lose, I don't know, 0.001% in terms of performance, or it's going to lose 50% of its performance. So that's the concept of technology robustness. And the idea is that every new technology is more performant, but since it's new, it's less robust because it didn't have time to be tested, okay? Testing and making mistakes and correcting mistakes, it's a very important step in technology evolution, okay? So that's what happens if you look at robustness measured by durability, cost, interchangeability. That's another very important concept. Interchangeability is what we know as drop-in in terms of fuel, okay? How are our fuels interchangeable, okay? So every new technology brings a loss of robustness, but with time, with evolutive development, eventually it will, okay, get better. So, how does this model apply to the development of liquid engine fuels? Let's try to focus on our problems here, okay? My point is that, well, if talking about auto cycle engines, okay? My point is that we have gasoline. Here in Brazil, we had a lot of first generation ethanol. And my point is that second generation ethanol, we are more or less like here in terms of performance. And by performance, you can measure this many different ways: energy balance, ecological footprint, performance with specific engines. So my point is that we are more or less here. We have first generation, we have second generation, but there's something important here. Gasoline, fossil sources, okay, I think it's going to probably be on the scenario for longer time, especially due to, I'm going to show you why, because it's still very cheap, okay, and also because CCS technology may play an important role, okay, and in terms of robustness, we may be more or less like here, okay, so we are less robust than in the, I would say, 1968. Before the first oil crisis in 73, okay? So at this time, 68, we would be probably here, or actually here, okay? And now we have many different types of fuels and being made from many types of feedstocks. So, in my opinion, there's a lack of robustness, okay? So if that's the point, let's see how these things are done in our case. I want to talk about what we call the agro-industrial system, okay? But first, let's know the enemy, okay? Let's know the enemy. How things work, because I'm saying that gasoline and diesel and so on, they are still very competitive. Actually, they are beating us. We're not that competitive. Right? So let's take a peek at the enemy. So what happens when you produce oil? What's the production system as far as oil is related? You have, well, a reservoir here. You drill a hole, and you have oil seeping to the pipeline, okay? And then, well, you can put that in a tanker and ship that to wherever in the world, Brazil, for instance. Okay, but the point here, what I want to highlight is that the main cost of concentrating the production in one point, that's a logistic problem, okay, occurs only once during well boring. Okay, and why is that important? Because it enables economies of scale. Okay, you can scale up. Become bigger and bigger and bigger, and you become more competitive. And now let's see the agro-industrial system. The problem is with agro-industrial system that is a biomass production system, and the point is that it is always distributed over the production area. You're going to spend energy, spend money to concentrate the production to the point of industrial processing, for instance. So typically, this kind of industrial systems are medium to small scales compared to the oil industry, okay? And, well, it may be bigger or smaller depending on the added value of the product, okay? I know a project, for instance, I'm working on with this, we're extracting tannins from acacia bark. Okay, so it's a very interesting product from the money point of view. So you are able to cultivate a larger area when you compare this to sugarcane, for instance. Okay. Well, this agro-industrial system, if we look at this in details, what is it? It's a cultivation area. Okay. An industrial unit, and a logistic problem. So you have these three, I would say, class of problems to deal with, okay? And we know that, well, this is mature technology. First generation here in Brazil is already mature, yeah? We have an average cultivation area. We know the amounts of biomass that we have to process. Well, this is for the guys from the agricultural people, okay, and this is to industrial people. You know, you have to think in terms of processing rate, 500 tons per hour. This will define more or less the size of your equipment. Well, you know all this data. This is here in Brazil, this is first generation, is already TRL 9 because it's being done for the last 50 years. So we have this kind of what we say turnkey contracts, and we know even how much it's going to cost. Something, a sugar mill like this, something around $200 million, which is, I don't know, the cost of two A300 or half Boeing 747, $400 million, Boeing 747. So it's very known stuff, okay? The point here is that incorporating new technologies increases the upper viability limit and therefore the overall economicity. So what I'm saying is that we need to incorporate new technologies in order to increase our scales, in order to be more competitive, in order to win the battle, let's say, against fossil sources. So in the production area, you can genetics, planting machines. I'm going to be talking about this in a while, okay? What I wanted to, I have a few minutes still, but I want to tell you about this, okay? A case study, okay? So let's go. But first, let's know the enemy. One thing I organized this presentation thinking of this saying by Sun Tzu, okay? We must know our enemy and ourselves. We're here to know ourselves, okay? We come to this kind of congress, I talk to my peers and I see what they are doing, we can discuss, so we know ourselves. But my point is that we have to know the enemy, okay? Because if you know both, we don't need to fear the result of 100 battles, okay? If you know yourself but not the enemy, for every victory gained, you will also suffer a defeat, okay? Because the enemy is still, probably right now, there are people in some room talking about petroleum extraction and so on. So they're not sleeping, okay? And if you know nothing, go home and change your job, okay? So that's the point. Let me give you a scenario. Okay, this graph shows the proved petroleum reserves. Just to give you a scale. So this is the amount of petroleum that we can exploit. Okay, this is reserves. Okay, and the black line here is, I think it's very complicated in terms of billions of barrels. I cannot figure this. So my unit is Saudi Arabia. So Saudi Arabia is the black line. You see in the Orinoco Bay was found a very huge petroleum reserve. So you have a second Saudi Arabia waiting to be exploited. And you know perfectly why it's not right now being exploited, okay? So you have a lot of oil. This is a discovery, actually, but you see the influence of bituminous sands in Canada, the development of the corresponding technologies. You have another Saudi Arabia, a leap corresponding to all Saudi Arabian reserves. When we talk about gases, the unit's not a Saudi Arabia, it's Russia. They have so much gas there that's, especially in the permafrost, it's starting to bubble and make these huge craters here. And you see between Qatar and Iran, just before the Strait of Hormuz, there's this field, North Field, huge amount of gas. Qatar is already exploited, but Iran, no, it's still a reserve. Okay, so you have a lot of oil and gas. And all this oil and gas is becoming, let's see, in terms of use, gasoline, 38%. The importance is the application, okay? Diesel, kerosene, oil, natural gas, electricity. Electricity is basically for trains and trams, okay? But other liquids, I'm ashamed. We are other liquids, 0.6%. So that's terrible. That's our fight. That's our battle. So that's why we're taking a look at the enemy, okay? So let's see let's draw some conclusions about the scenario, knowing ourselves and knowing the enemy, okay? The anticipated decline of the world's petroleum and gas production, according to Hubbert's law, have been proven premature, okay? We know that petroleum is going to end someday, but it's still going on. I just show you slides. You have several Saudi Arabias to be exploited, okay? Renewable energies compete economically and technically with fossil fuels. In addition to competing, biofuels must adapt to the existing infrastructure developed originally for petroleum products. That's the drop-in concept, or interchangeability I just mentioned, okay? Also, fossil sources will continue to be exploited with consequent intensification of CO2 and possibly other greenhouse gas emissions, okay? And that's why CCS, remember the quixotic idea of putting supercritical CO2 in the underground, because, well, biomass may be not as competitive in terms of producing a fuel for internal combustion engine, but I'm sure it's the most competitive carbon carrier, okay? So our biomass plants may be actually CO2 captures, okay? Let me show you how this is working in a particular field, which is the transportation sector. Transportation, you need, what's the purpose? What would I ask for Santa Claus? Well, I want to go as fast as possible and spending the minimum as possible energy. So if I make this operation envelope, plotting, okay, the speed and the energy consumption, the ideal region is here. Here's Santa Claus, okay? And if you make the survey and plot the transportation in this envelope, you get this for passengers and you get this for freight, okay? And you see something strange is happening. There's a void here, okay? There's a void here. Why is that? That's nature. You can't get something for nothing, okay? If you're going fast, you're going to spend a lot of energy. If you allow to go very, very slowly, like in a tanker, okay, you may be able to spend small amounts of energy, okay? So this is a natural limit here, which is a kind of a Pareto frontier, and we know that there are some transportation technologies that are near this Pareto frontier. That's those big airplanes or road trains and tankers and super tankers and super containers, okay? So what do we need to make fuel for is for this kind of transportation machines, let's say like this, okay? We don't need to make fuel for supersonic aviation, except for military. Okay, the Concorde, it's not going anymore, okay? But we need to make fuel for these applications here. So let's ask ourselves, yeah? Oh yeah, or time machines. Yeah. So let's ask ourselves if will biofuels displace fossil fuels in the transportation sector? The transportation sector, I hope to have characterized the transportation sector with this slide. Okay. So will it displace fossil fuels? I don't know. The application in terms of division. Okay. So you have motorcycles and cars. This is fuel for auto cycle, okay, internal combustion engines, okay. Heavy trucks, here you have diesel cycles, okay. That's a very different kind of fuel, a different kind of application. Aircraft, you have to make kerosene. Well, light trucks, they may work fine with gasoline or ethanol, okay, and other less important application in terms of size. Okay, so diesel engines, biofuels for high power engines. In high power, I mean more than 1,000 horsepower. Okay, for a huge 1,000 HP, it's a big wheat harvester has an engine of this size here. So it's not for light trucks. It's very heavy machines. So these are still in the early stage of development, but mainly due to feedstock issues, food versus energy. Okay, that's really because it relates to the price of food. Biokerosene for a Brighton cycle is still in the process of technological development associated with its certification as an aviation fuel. Aviation fuel, the mission conditions, the environment is very, very complicated. It's going to, the temperature, for instance, it's going to change between, I don't know, 40 degrees on the ground in the airport and to minus 60, minus 50 at 30,000 feet high. Okay, so the temperature difference is very high. You can figure that you have small ices, and you can imagine the kind of problems that you can have. Okay. Another point here is that industrial process of biomass conversion to biofuels for auto cycle engines must evolve to 8 and 9. Okay, and here I mean specifically second generation technologies. Okay, and overall economicity must be improved by integrating new technologies to enable large scale systems. That's the point. Okay, large scales in order to be economic. So just I'm almost done. Okay, so let's see our scenario today. Initiatives in the world and so on. So, you know, this is compiled by Task 39, the International Energy Agency, and if you can do it yourself. The link is here. Okay, and if you ask for everything from this database, so this is related to liquid biofuels industrial installations. Okay. So let's try to narrow this down. Okay, so now here you have all types of technologies, gasification. This is a thermochemical conversion. Okay, so I want only those that are operational, only those that are mature. Okay, and only those that relates to fermentation. Okay, already TRL9 and in operation. Okay, so you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, if you do the same for oil and gas, do you know that? And I wasn't able to put Asia in the picture here. Okay, but you see, this is the North Field between Qatar and Iran. So that's the scenario too. That's why we are only 0.6%. So, and that's what we are proposing to displace. We want to occupy these red dots. They must become green dots. So you see the size of the task. Okay, so there's no surprise. You have seen this picture before. Non-renewables is almost, I don't know, 100%, 99% of the supply. And this is why. Why is this? Because we have literally hundreds of years of experience. Many people contributed to this scenario. For some, you know, Rockefeller was the first guy to identify that scale was everything. So he started buying small companies and making bigger companies. So he started to benefit from the economies of scale, and he became the richest person in the world. If you want to compare, it's like having, you know, you can think of a millionaire today, Bill Gates, okay, or Bill Gates. Rockefeller was something like 4 or 5 times richer than Bill Gates, okay? But it's hard to compare because they are 100 years apart. But his contribution that I'm highlighting is the scale, the necessity to be very big, okay? Another guy that had an important influence here was Churchill. In the beginning of the century, he fought to change his ships, his battleships, from coal to petroleum, okay? And why is that a problem? Because, you know, UK has a lot of coal, but they don't have oil. So, but the advantage is that the ship ran with oil, the performance is much better, okay? but they don't have oil. So they went, and the United States had a lot of oil, but, well, they are independent. That's what's going in his mind. And so he went to the Middle East. And then he found Mr. Caluste. He was a very well-related guy, and he knew all the royal families. And so he opened the Middle East for European companies, and he was known as the Mr. 5%. That's a true story. Okay, no problem. We're going to make this business, but 5% in my pocket. Okay, and his nickname was Mr. 5%. Okay, but that's the scenario today. We want to change it. This is Energy Outlook from 2017. Possibly in 2047, we're going to have 99% of renewables. The new Rockefellers, and, well, not the new Mr. 5%, but the new Rockefellers and the new Winston Churchills are possibly among us, okay? So let's try to see how this can be done. Very quickly, those three problems: production, logistics, and processing. You have several examples of new technologies. For instance, you can try to apply what we call a whole harvesting technique. Instead of, if you see, separating the softer parts of the plant from thrash and straw, okay, and then after this you have several agricultural operations. If you put everything together, and if you have an efficient stationary separation technology, well, this is going to be a lot more economic because you have no need for tedding, for baling, and so on, okay? If you do this and you develop through genetic modification, for instance, a plant that has very robust roots, and or you develop low soil compaction tires, okay? So you go, instead of having these wagons here, you go with your truck directly on the fields, no problem, and then you can avoid transshipment, for instance, okay? And in addition, if you have geometries appropriated for this kind of road trains or road trucks, okay? In Australia, you know, you have 12 wagons, 10 wagons. Here in Brazil, we are used with 3 wagons, and this is related to how roads and lanes are made. Okay, but so if you manage to do this, low fuel consumption, okay, and if you manage, for instance, just to give you an example of a new technology inside the industrial limit here, okay, high performance extraction, especially because here you can have, for instance, sugarcane bagasse with traditional extraction has roughly 2% residual sucrose. What will happen in this path? What will happen with 2% sucrose in pretreatment, in hydrolysis, and so on, okay? It may be a problem, but if you develop a high performance extraction, so you are sending, I don't know, 0.1%, okay, and it will enable this deviation here, okay? So that's an example of how we can incorporate new technologies and, well, gain with, especially in scale, okay? So the point is, learning through experience naturally drives improvement through reinforcing feedbacks to technology reevaluation at all levels, okay? And I showed you a lot of obstacles and problems and so on, but the idea is not to demotivate you, is actually exactly the opposite, because these problems are opportunities, okay? So let's embrace them. Thank you very much. Yeah. So our next speaker, Professor David Caramonte.